Hello, we are ready to start Chapter 8, which is on alkyl halides, also known as haloalkanes. Those two phrases mean the same thing. One's more of an IUPAC way of naming, the other is more of a common way of naming, but we'll get to that in a later video. Today, we're just going to talk about what are alkyl halides and what are not alkyl halides. Just because you have a halogen doesn't necessarily mean you're an alkyl halide. So that's what this short video will be about today. I would suggest that you stop and read page 286 in your book first, and then come on back and view the rest of the video. What are alkyl halides? Well, alkyl halides have a halogen, obviously, and they must have that halogen bonded to a saturated, or sp3, which, as you know, is tetrahedral carbon atom. No oxygens, nitrogens, or anything else on that same atom. It's possible they could be elsewhere in the molecule, but not on the same carbon with the halogen. Now, why is that the requirement for alkyl halides? Well, as we will see in the next chapter, they undergo a reaction called nucleophilic substitution. So real briefly, some molecule, which we're going to call a nucleophile, again, don't worry about exactly what that is just yet, except it has to have a pair of electrons, that can share that pair of electrons with the carbon that had the halogen on it. But at the same time, the halogen has to be able to leave. So the nucleophile comes in on one side, the halogen leaves on the other side. In order for that to happen, you have to have 3 other single bonds on that same carbon. In the process then, as the halogen leaves, the nucleophile attaches, we have a new bond here, it flips over the other 3 groups like an umbrella in the wind. So just a quick reminder that we already covered this reaction, at least one example of it, in the previous chapter on alkyne synthesis. So you may remember that if you take an acetylide and react it with an alkyl halide, you get an alkyne. We looked at it from the point of view of the acetylide in the last chapter. Now we're looking at it from the point of view of the alkyl halide, but it's the same reaction. So if you have an alkyl halide, that is a carbon with a halogen and 3 single bonds, then that's subject to this reaction. And if the nucleophile, which really just needs to have a pair of electrons, is the acetylide ion, in this case, it can come in and attack that carbon and push out the halogen. So let's review the 3D model video that we looked at back in that chapter. So there's that lone pair of electrons there that makes that carbon negative, and the lone pair of electrons that's represented by a pair of dots is now represented by a stick sticking out. And then we're going to bring in the alkyl halide, and the alkyl halide in this case is methyl chloride. The green ball represents chlorine, but it would work just as well if this were bromine, and if one of these 3 balls with some other carbon group, it would work just fine. And literally what's going to happen in that second reaction is that the acetylide is going to come in from the back, and it's going to donate its pair of electrons onto that carbon right there, and at the same time, the halogen is going to leave with its pair of electrons out the other side. And then, here comes the group in, and it attaches on the back of where the halogen was. So the halogen has just left from this side right here. The hydrogens have flipped over like a umbrella in the wind. That's one possibility. The other possibility is that the carbon may lose its halogen directly without any nucleophile attacking. In other words, this pair of electrons just goes off onto the halogen, forms an X minus, as it did here, and leaves that carbon with a positive charge, which then is sp2 hybridized and flat. But in order for that to happen, it had to have the 3 other single bonds there to begin with. So those are the 2 ways in which alkyl halides will react. Again, we'll learn that in the next chapter. But obviously then, to be an alkyl halide, you have to have those 3 other single bonds there to start with, which means you have to be sp3 hybridized. Now, some molecules that have halogens but are not alkyl halides, well, these are called aryl halides. In other words, if the halogen is directly attached to the benzene ring, it cannot do either of those 2 processes, and so it's not an alkyl halide. Those, by the way, are also called haloarenes. Again, we'll deal with them in a later chapter on benzene rings. Vinylic halides are those that have a halogen directly attached to an alkene double bond. By the way, this has a halogen directly attached to the double bond, but it's not an alkene, it's an aromatic. So this is a different case, even though it looks the same. The halogen cannot be attached to a carbon-carbon double bond of an alkene. Those do exist, they just are not alkyl halides. They're called vinylic halides, alternatively called alkenyl halides or haloalkenes. And then finally, you cannot have the halogen directly attached to a carbon with a double bond O, because those are called acyl halides. They do lots of useful reactions, but not the ones I outlined for you, so they're not considered to be alkyl halides. They're called acyl halides, and that's because this group with a C double bond O and some other carbon group attached is called an acyl group, so this is an acyl halide. So why are these not alkyl halides? Again, because they cannot undergo those two processes I mentioned before. They can't be attacked from the back, so they can't do that first of the two processes. And they also form terrible carbocations, so they can't just lose the halogen to form a positive charge. Again, a lot more detail about those later. So, some molecules that are alkyl halides. Well, I've made some models and I've drawn some structures here. This is a CH3 with a bromine attached. Here is the ball and stick figure for it. Just a chlorine, which is green, and a methyl group carbon with 3 hydrogens. So that's an alkyl halide. I've also made a space-filling model of that just so you can see the sizes. So notice that the methyl group is just a little bit bigger overall in size than the chlorine itself. Chlorine is like a big green thumb sticking out from the side. This is a ball and stick model of a molecule that's not an alkyl halide, because notice the halogen, again, green ball represents chlorine, is attached to a carbon with a double bond. So this would be a vinylic or an alkenyl or a haloalkene, but not an alkyl halide. However, notice this molecule is an alkyl halide, even though it still has a carbon-carbon double bond in it. The carbon with the chlorine attached is a saturated carbon, sp3 tetrahedral. So this is an alkyl halide, even though it has a double bond. That is this molecule drawn out as a structure. So notice carbon-carbon double bond. Then the carbon next door has 2 other hydrogens, so a total of 4 single bonds on that carbon. And so that is an alkyl halide. Just for comparison, I made a model of, besides methyl chloride, I made a model of methyl bromide, and you can see the brown ball representing bromine is even bigger, about the same size as the methyl group now. And finally, this happens to be methyl iodide. Notice that great big brown iodine atom attached there. So that's methyl iodide. Here's some other ones. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons with an iodine on the 4th carbon. When we learn naming, you'll learn that that's called 4-iodo-nonane. And it's an alkyl halide because the carbon the iodine is attached to has a total of 4 single bonds. In other words, it's sp3 and tetrahedral. This is ethyl chloride. Has a carbon with 4 other bonds to it with a chlorine on it, just to show you that the halogens can exist on rings as well. This is chlorocyclopentane, and that's also an alkyl halide. I made a couple more models here. This is purple ball to represent iodine, and so this is a alkyl halide. The iodine's on a saturated carbon. This one happens to be isopropyl iodide. And this one has a bromine represented by an orange ball on a 2-carbon chain. So this is ethyl bromide. Again, alkyl halide because the carbon is saturated, has 4 single bonds to it, sp3 hybridized tetrahedral. Thank you for your attention.